let me tell you about this paper. So this work begins with two observations. The first observation is that people only have a limited amount of time in which to make decisions. That might be a few seconds, could be a few days, could be a few years. There's always some limit. The second observation is that making good decisions can be time intensive. And what I want to do in this work is explore the implications of these two observations for behavior. Now, the available empirical evidence suggests that people respond in part to time constraints by using behavioral heuristics. And these heuristics are simple rules that help us make complex decisions quickly. An example of a heuristic that will be especially important in this work is choice bracketing. And roughly speaking, choice bracketing says that when a decision maker faces multiple different decisions, she'll make each decision without considering the rest. And this is something that has had widespread empirical support both in the lab and so I want to start this talk with an example of choice bracketing, and then I want to try to understand it from a computational perspective. So this example of choice bracketing comes from a 2007 AER paper by Ferrer and Goethe. And these two authors run a field experiment working with two Swiss bike messenger companies. Right? So bike messengers are basically delivering letters or small parcels from one part of a city to another. The way these firms work is that the bike messengers sign up for daily shifts of 5 hours. And then within each shift, they're paid per delivery that they complete. So for example, if a bike messenger pedals the bike faster, puts in a lot of effort, they might be able to sort of earn more on a given shift. Now, what these authors do is they randomize the wages that the bike messengers are paid per delivery. And interestingly, what they find is that when the bike messengers are paid higher wages, they actually put in less effort per shift. Now, this is counterintuitive, right? So from a sort of standard classical economic perspective, what we would say is that, okay, well, if you're being paid more per unit per delivery on Monday and less per delivery on Tuesday, you want to put in a lot of effort on Monday and consume more leisure on Tuesday. But that's exactly the opposite of the pattern that these authors find in the data. So the authors argue, and they provide additional experimental support to experimental evidence to support this, that the behavior of the bike messengers is consistent with what's called a daily income target. Right? So for example, a bike messenger would say, okay, I want to earn $300 today, and I'm going to pedal my bike just quickly enough to complete enough deliveries to make that $300. This would lead to the pattern of behavior that we see in the data. But it's also odd, right? And it's odd in particular because it involves this daily frame, this daily bracketing. When I'm making my labor supply decision on Monday, I'm not thinking about my labor supply decision on Tuesday. So let's try to understand this behavior from a computational perspective. And I'm going to make the example a little bit more concrete, introduce some notation. Let's suppose that we have a worker, and on any given day I, the worker is going to decide whether to put in high effort or low effort. I'm going to note the effort decision by capital XI and the day by I, there are n days in total. Now, one kind of behavior that the worker can engage in is to plan one day at a time. This is what we saw in the previous slide. And one algorithm that we could imagine workers using to plan one day at a time is to simply search over the two actions, high effort or low effort, on any given day, decide which one they prefer, and then repeat this for the remaining days. This algorithm will take an amount of time to reach a decision, which is growing linearly in the number of days. And we're going to think about linear time algorithms as being reasonably quick, right? So in other words, it's a plausible algorithm that people could use to generate that behavior. On the other hand, if we were to write down sort of a more classical economic model, make more traditional assumptions, we might say, okay, no, the worker is going to not plan one day at a time, but plan all n days at once. So consider what they're going to do on Tuesday when they're deciding how much to work on Monday. Now, one algorithm that the worker could use to plan n days at once is to search over all the vectors x, where vector x denotes on any given day I, whether the worker will put in high effort or low effort. Now, there are 2 to the n such vectors. And so the amount of time that this algorithm will take to complete is growing exponentially in the number of days. Now, exponential growth is extremely aggressive, right? So even if the worker has the processing ability of a modern computer, very quickly as you increase the number of days, the amount of time taken to complete this algorithm will exceed the lifespan of the worker. So we're going to think about this behavior or this algorithm as being not plausible. It's not a plausible way to generate the hypothesized behavior. Of course, we want to be careful, right? We don't want to say that planning n days at once is not plausible because maybe there's a quicker algorithm that manages to exhibit that. So this example is going to motivate both the research question and the approach that I take to answering that question. My research question is, are behavioral heuristics like choice bracketing necessary responses to computational constraints? And the way that I'll model computational constraints is I'll ask whether there exists a reasonably quick algorithm that generates the hypothesized choices. Now, let me give you a little bit more of a preview of the framework and the main results in this paper. So the key definition is computational tractability. So I'm going to say that choices are computationally tractable if there exists some algorithm that generates those choices in at most polynomial time. Now, this is intended to be a conservative definition, right? So there's certainly behaviors that can be done in, say, linear time, like adding two large numbers, that are hard for people in practice. But what I want to get at here is sort of a notion of tractability that really only rules out behaviors that we are confident are fundamentally hard to exhibit. Now, the question is, with a conservative definition, what results can we try to prove? Well, I'm going to give you two sets of results. The first ones are going to show that under standard assumptions, behavioral heuristics are necessary responses to computational constraints. So more precisely, I'm going to show in my first three theorems that if choices are computationally tractable and satisfy the expected utility axioms, then they are observationally equivalent to forms of choice bracketing. So this sort of combines a very standard set of axioms from decision theory with this additional assumption of computational tractability and gets a very strong implication for behavior. Now, the next result takes a step back and asks, in the presence of computational constraints, are these standard rationality assumptions, the expected utility axioms, even still appealing? And what I argue is the answer is no. So given computational constraints, I argue that standard rationality assumptions are not always normatively appealing. More precisely, my theorem 4 will say, for a decision maker who intrinsically wants to maximize the expected value of some objective function, there exist heuristics that violate the expected utility axioms, but perform better than any tractable choices that are consistent with those axioms. So in other words, a decision maker might be objectively better off if they're willing to make choices that an outside observer looking at those choices would say are not rational. Okay, so those are the results. I'll defer related literature since it's a short talk. And I'll move on to the model, and then I'll talk a bit about the results. Okay, so the model starts with a single decision maker who cares about some outcome. An outcome is some variable x in some set script x. Before I formally define outcomes for you, I just want to give you sort of two examples to keep in mind. So you can think about x as a consumption button, where it's a sort of high dimensional vector where xi is the quantity consumed of good I. Or you can think about x as income from some investment portfolio, where xi is the income earned from asset I. Now, what's important about these two examples is they're both high dimensional, right? So if you go into a grocery store, you'll see tens of thousands of different products. If you're an investor in the New York Stock Exchange, you'll see almost 3,000 different assets listed, firms listed, right? So in either case, you would expect to see the dimension of the outcome to be on the order of 1,000, 10,000. Right? This high dimensionality is going to play a critical role in sort of generating the, capturing the complexity of the decision that the decision maker is facing. Now, formally, I'm going to let the set of outcomes consist of what I call eventually zero sequences. These are infinite sequences that are zeroed out after a certain point. So an infinite sequence where there exists some number n, some dimension n, such that the first n coordinates are take on some arbitrary value, and then the remaining coordinates n plus 1 and onwards are 0. Right? So these are outcomes that are technically infinite dimensional, but effectively finite dimensional. And it's going to let me think about sort of arbitrarily large but finite dimensional outcomes. Next, let's talk about choice. So decision maker doesn't get to choose outcomes, right? So an investor does not get to choose how much income they earn from, say, Apple shares. What they decide is how many Apple shares to buy, and that will be stochastically linked to some income. So the choice that the decision maker is making is over what we call lotteries, and these are simply random outcomes. You can also think about a lottery as a random vector, where each coordinate of the vector corresponds to what I'll call a partial lottery, where so xi is the realization of the first coordinate of the outcome. Now, one thing that's important to note is that the different partial lotteries could be correlated, right? So my returns from Apple shares could be correlated with my returns from Tesla shares. Next, we'll talk about menus. So menus describe sort of the set of feasible options for the decision maker. A menu M is simply a finite set of lotteries. And it belongs to some collection, script M, of menus. This is like the universe of problems that the decision maker could face. Finally, we'll define a choice correspondence C. Choice correspondence is going to map a menu in our collection of menus to some lottery within that menu. Okay, so I need to give you a little bit more detail about two things. I need to give you a bit more detail about menus, and I need to tell you what rationality assumption we're going to impose on the choice correspondence. So start with menus. A typical assumption is sort of what we'll call richness assumption, is that the collection of menus includes all binary menus. So menus consisting of at most two lotteries. To say anything interesting in a setting like this, we need to sort of suppose that the decision maker, might actually be facing some decisions. And so this assumption says that the decision maker should be capable of making a choice when faced with any binary menu. Now, that's not going to be quite enough in our setting, because we want to think about a decision maker that's sort of making many different decisions at the same time. But we'll basically do a high dimensional analog of this assumption that says the decision maker doesn't just face a binary menu, but they face sort of many different binary decisions. So a partial menu, just to introduce some terminology, a partial menu MI is a set of partial lotteries XI. So it's like, how many units of Apple share you can buy if I corresponds to Apple share. A product menu is simply the Cartesian product of partial menus. The important property here is that what I choose in dimension I does not affect what's feasible in dimension J. And then the assumption is that this collection of menus includes all product menus with binary partial menus, right? So I'm faced with many binary decisions. Importantly, this is an assumption that says that if the decision maker were faced with a menu like this, that she would be capable of making a choice. It's not necessarily ruling out the possibility that the decision maker faces other kinds of menus as well. Okay, and then finally, rationality. So I'm going to say that choices C are rational if they can be rationalized by preferences that satisfy the expected utility axioms, or equivalently, if there exists a utility function U mapping outcomes to real numbers, such that the choice appears as if it is maximizing expected utility. Okay, so we've talked about the basic decision theoretic model, and now let's introduce computation. Let me start with a quick diagram. Oh, actually, no, because I wanted to save time, I got rid of that diagram. So you will unfortunately not be treated to the diagram of the server presenting wine to a customer in a restaurant. Instead, we'll dive right into the definition. So I'm going to say that choices C are tractable if there exists an algorithm A, where first, the algorithm takes in a description of the menu that the decision maker faces and outputs a choice that the decision maker would have made. And second, the algorithm is reasonably quick. So it halts in a number of steps. It's growing at most polynomially in the dimension of the menu. So in other words, the number of assets to be purchased or the number of products in the grocery store. So choices are tractable if there exists some algorithm that could have generated your choices in a reasonable amount. Okay, so with that key definition, let's move on to the first set of results. These are the results linking tractability plus standard rationality assumptions to choice bracketing. Now, to start, we're going to think about the set of rational choice correspondences depicted in the blue oval. And we want to think about the intersection of that with the set of tractable choice correspondences depicted in the red oval, right? That intersection, that purple region, is a set of choice correspondences that are both rational and tractable. It's a region where rationality is compatible with tractability. Now, I'm going to start by simplifying the problem a little bit. So we want to eventually characterize that intersection, but let me start by characterizing an even smaller intersection, which is the set of rational, tractable, and symmetric choice correspondences. Now, this intersection, I will argue, corresponds to narrow choice bracketing, or equivalently, it corresponds to maximizing expected utility as if you have an additively separable utility. So let me be more precise about that. The representation theorem. So first, we need to define symmetry. So I'm going to say utility function U is symmetric if the arguments are interchangeable. So in other words, if you switch xi with xj and xj with xi, you're going to get the same utility. This is plausible in some settings, but not in others. So in the context of investment, maybe you think that like, a dollar earned from Apple is the same as a dollar earned from Tesla. But in the context like consumption, probably the number of apples you have is not, interchangeable with the number of oranges you have. Nonetheless, it's a useful simplifying assumption to start. I'm also going to assume that P is not equal to NP. So probably most people in this audience will know of this computational hardness conjecture. Theorem 1, if choices C are rational, tractable, and symmetric, then they can be rationalized by an additively separable utility function. Right? So the definition of additive separability is depicted below. Of course, given symmetry, you would expect these UI, U1, U2, U3 all to be the same. So we started with all possible symmetric utility functions. Then we added tractability, what I've argued is a relatively mild computational constraint. And we've got a very strong restriction, functional form restriction on the preferences of the decision maker. Now let's map this back to choice bracketing. So first, let's define choice bracketing. Narrow choice bracketing, which is really only defined on a product menu M, optimizes over partial menus MI separately. So in other words, it says, okay, let's focus first on my partial menu M1. Let's think about the set of partial lotteries X1 that are available there, maximize some utility function U1, and then move on to the second decision, second partial menu, the second partial lotteries. Or similarly, I might sort of focus first on deciding how many Apple shares I want to buy. And then only then I will think about how many Tesla shares I want to buy without sort of considering the interaction between these two. Now, narrow choice bracketing can lead to all kinds of what you might think of as odd behaviors. So correlation neglect, for instance, in investment, or small stakes risk aversion, but not that sort of more the large stakes risk aversion that we usually have in mind in economic models, or sort of an imperfect intertemporal substitution of things like labor supply, as we saw in the bike messenger example. So all kinds of behaviors that would seem odd from a very classical perspective. But what we can observe quite easily is that on product menus, narrow choice bracketing is observationally equivalent to expected utility maximization with an additively separable utility function. Right. So another way to phrase that last statement is on the last theorem is on product menus. If choices are rational, tractable, and symmetric, then they are observationally equivalent to narrow choice bracketing. All right. Now, we made an assumption, the symmetry assumption, which is perhaps too strong. And ideally, what we would like to do is we would like to characterize the intersection of rational and tractable choice correspondences without this symmetry business. Now, again, given time constraints, I'm not going to go into too much more detail, but my theorems 2 and 3 provide a characterization of the intersection of these two sets. So what I show is that rational tractable choice correspondences, they don't correspond to narrow choice bracketing, but they correspond to a generalized form of choice bracketing that I call dynamic choice bracketing. And really what this is going to do is it's going to combine principles of dynamic programming with principles of choice bracketing, right? So choice bracketing, the idea that you're going to focus on only a small number of decisions at once. Equivalently, so just as we related narrow choice bracketing to additive separability of the utility function, we can relate dynamic choice bracketing to what I call Hadwiger separability of the utility function, right? So this, like, dynamic choice bracketing is sort of a new concept that was that came up in the paper. It's a graph theoretic characterization of utility functions that basically says, in the context of like purchasing products in a grocery store, you might have some complementarities or substitutabilities across products, right? Like maybe you see peanut butter and jelly as complements and like beef and lamb as substitutes. So you might have some complementarities and substitutabilities, but their frequency should be limited in a particular way. Now, again, I'm not going to go into too much detail, just in the spirit of meeting time constraints. Okay, so then we've talked about the results that link tractability to behavioral heuristics. Now let's take a step back, move on to the second set of results, which ask, given tractability, is rationality as we usually define it even and still a normatively appealing concept? So to answer that question, let's think about optimal behavior under computational constraints. Here, let us say that we have a decision maker, and the decision maker cares about the expected value of some objective function u bar. An objective function is just like a utility function, so it's a map from outcomes to real numbers. But unlike a utility function, we're not thinking about this as something that is revealed through your behavior. We're thinking about this as something intrinsic. This is what you care about for whatever reason. Now, we know from the results that I showed and did not show you that if the objective function is not Hadwiger separable, then exact optimization is not tractable. But you're still, still have to make a decision. And so if you're computationally constrained, if you cannot do things that are, NP hard, then you might try to come up with choices that are at least approximately optimal in some sense. Right? And so we're going to think about a decision maker that's looking for approximately optimal choices. And the question we want to ask is whether an outside observer looking at this decision maker's choices, whether they would conclude that the decision maker is rational. Now, to answer this question, I need to, of course, tell you how I'm going to define approximately optimal choices. So, oh, excuse me. Again, shortening the slides, cutting out all the material that I'm so used to from, the half a year of giving this talk nonstop on the job market. So approximately optimal, and I think this is probably fine for this audience, approximately optimal means gives a good worst case approximation, right? So guarantees, say, 50% of the maximum payoff. And of course, it has to be done in polynomials. So that's what I mean by approximately optimal. And also to clarify, when I ask whether an outside observer would conclude that the decision maker is rational, what I'm asking is so that decision theoretic, the econ question of, does there exist a utility function u that rationalizes the choices? Right. So even if I can rationalize my choices using a utility function that is different from the true objective, whatever that may be, even in that case, decision theorists, economists would tend to call that rational. At the very least, it would satisfy the axiomatic definitions of rationality. So without further ado, let me show you the result. So the result says that rational and tractable choices are not approximately optimal, and vice versa. So tractable and approximately optimal choices are not rational. I'm going to make a slightly stronger computational hardness assumption. NP is not a subset of poly. And then I'll give you the following theorem. So theorem 4 says there exist objective functions u bar such that, first, no rational and tractable choices are even epsilon approximately optimal for any epsilon greater than 0. So if you restrict attention to choice correspondences that are rational in addition to tractable, you cannot get any constant approximation to your true objective. Now, maybe this just means that the problem is hard. That in itself doesn't say anything positive or negative about rationality as a concept. But the second result is that there do exist tractable choice correspondences that give a one half approximately optimal. So there are algorithms for the setting that give you a half approximation, two approximation, as computer scientists would say, polynomial time, but they're not going to generate patterns of behavior that are consistent with the expected utility. Okay, so in that sense, they're not going to be rational. Now, one question you might ask is, okay, these objective functions, maybe they're very pathological, maybe they're rare, maybe they don't represent the typical kinds of economic decisions that people might face. But actually, this holds true for even very benign objectives. So for example, if your objective, if you're an investor and you care about the total sum of income across all assets, but you're risk averse, so maybe you care about the square root of the total income, then this result will hold. Right? And there are many other objective functions that are quite natural for which this result will hold. So let me conclude by just summarizing the results that I showed. And I'm going to summarize them using a diagram that I called the choice trilemma. So we began with these two concepts, rationality and tractability, and we characterized their intersection as corresponding to dynamic choice bracketing. Right? I told you about narrow choice bracketing, and I alluded to a more general result on dynamic choice bracketing. Then we talked about approximate optimality. So the intersection of tractable and approximately optimal choice correspondences you can think of as approximation algorithms. Finally, we can think about the intersection between rational and approximately optimal. Now, this is a little bit less interesting, right? Again, rational says, does there exist some utility function that rationalizes your behavior, even if it's not the right one? Approximately optimal asks whether there is some choice correspondence that performs well according to your true objective. The only reason to think about this intersection is because I want to point out that this includes what we often have in the back of our minds in economic models, which is that the decision maker has some objective and they're exactly optimizing. Right? So they're not exactly optimizing some utility function that's completely different from what they care about. They're exactly optimizing their true objective. Now, my last theorem, it said that while you can obtain any pair of these properties, so you can have tractable and rational choice, you can have rational and approximately optimal choice, and you can have tractable and approximately optimal choice, you cannot have all three. So the intersection of these three sets is empty. And what that means for a decision maker is if you are computationally constrained, if you're not able to do NP hard things, which I think probably we're not able to do, then you have a meta choice. You can decide okay, do I want to make choices that would look rational to an outside observer? That's like checking whether I satisfy certain axiomatic conditions. Or do I want to be approximately optimal according to the objective that I actually care? And from my perspective, I would say probably people would prefer to be approximately optimal according to the objective that they actually care. Okay, and with that, just quickly highlight that there are many ways to think about applying computationally tractable choice to get tighter predictions, useful functional forms, to reevaluate existing assumptions, to obtain simplicity measures, and many interesting theoretical questions. I think Ryan is giving a talk after me, and he'll present some additional questions that I think are very related and worth pursuing. And with that, I will say thank you very much.